Thank you very much. And thank you very much for inviting me here. It is a big honor to present to you great community of Fairbanks some results or information of work which we are gathering this information at the Permafrost lab at the Geophysical Institute. And I will start with this information, what I will be talking about, is really a result of work of many, many scientists. First of all, our Permafrost lab at the Geophysical Institute, our university, which is truly international. We have scientists and students from the United States, from Russia, from Western Europe, from also from Asia. And also, in my presentation, I will use materials for much more many scientists, our colleagues from North America and international colleagues. So this is kind of a presentation which will show some results of our work, mostly related to changes in permafrost temperatures, but with some applications. What does these changes these changes mean for permafrost and for the Arctic? So first of all, I would like to, I will use cursor to point, because we have 3 screens, so it will be difficult to use a pointer. So first of all, a couple of words, what basic definitions. So what is permafrost? By the most common definition, and this is the map of permafrost distribution in Northern Hemisphere, the latest available map of 1997, and by the most common definition of permafrost based on temperature. So it says any earth material under ground surface with at or below 0 degrees Celsius temperature is permafrost. So pretty much any material which for 2 or more years. So you need 2 or more years of temperature below 0 to call this material permafrost. And we don't say that glaciers or multi-year sea ice is permafrost. No, it's not our sphere. So what we are talking about is material which is below the ground surface. And permafrost is product of cold climates. And you can see it from this map that most of the permafrost is in the high latitudes. In high latitudes and cold climates, and also is in high elevations. So for example, in Tibet Plateau, in China here, it's low latitudes but high elevation. So cold climate develop right conditions to permafrost to exist. And of course, when climate change, permafrost also react to these changes because it is product of cold climates. And in permafrost, if you look at the colors, we distinguish between continuous permafrost, which is farther north, and discontinuous permafrost in the south. And on this map, all blue colors is continuous permafrost, and all other colors are discontinuous permafrost. There is also interesting feature like subsea permafrost. Unfortunately, I don't have too much time to talk about it, but it's a very interesting object as well. So what is really interesting, and one of the most exciting feature of permafrost, of course, is ice in it. So it changes all properties when ice turns into water. That's why it's so exciting to look how permafrost changes with changes in climate and other conditions. So this is one of these examples. It may be a little bit extreme example where all this glancing, all this light color material is ice, and frozen soil is just in between. So by volume, this kind of permafrost, you will have much more ice than soil or ground, which is frozen as well and also has some ice in it. So the ice make permafrost is so special and so vulnerable to changes. You can imagine if you have something built on this kind of permafrost, what will happen to anything that is on top of it if this permafrost will thaw and ice will melt. So also another interesting feature is that most of the ice, most of the, we call it massive ice, in permafrost is formed as ice wedges. There's not only ice wedges which represent this massive ice. There are some other ones, like Pingo ice and other ones. But the ice wedges, which is, you can see on both pictures here, and taken from the same place in Siberia. So the ice wedges form this kind of polygonal structure on the top figure, this one, which will be important to understand what will be going on with permafrost when it will be thawing. And later in my presentation, I will show some results when this kind of permafrost is thawing and ice wedges are melting. So that's kind of remember this picture for the future discussion. And the lower part represents the same cliff, but you can see these ice wedges really form this kind of vertical bodies of ice, which could be several meters in width and many, many meters in depth, up to 20, 30, 40 meters, so more than 100 feet of ice. So permafrost could be really, really icy. In going to Alaska, and this is latest permafrost map which we developed towards the conference, permafrost conference, which we had in 2008 here in Fairbanks. So this is the latest map showing the, again, distribution of permafrost, continuous in the north, and discontinuous and sporadic in the south. And you can see that most of Alaska is covered or affected by permafrost. So just only some very narrow belt in the south, southwest, central, south central, and southeast are free of permafrost. Most of area in Alaska affected by permafrost. And this is kind of diagram I borrowed from USGS, kind of showing that continuity of permafrost. Continuous permafrost in the north on the left, and permafrost could be as cold in Alaska as -10 degrees and as thick as more than 600 meters, so more than 2,000 feet in thickness in Prudhoe Bay area. And then going towards Fairbanks and farther down south, permafrost change from continuous to discontinuous. And in Fairbanks area, permafrost is still present in large amounts, so more than 50% of area is affected by permafrost or underlined by permafrost in Fairbanks area. And then going farther south, the thickness of permafrost in Fairbanks area, typical one, around 50 meters, 150 feet on average, but it varies from just a few tenths of meters or even less, and more than 100 meters in thickness. And then going down south, we start to see some islands of permafrost only, which survived for some reason. Well, we pretty much know for what reason, but it's much less common than area without permafrost. And that we call sporadic or island permafrost. So that's kind of basic definitions, and with these definitions we'll proceed to the main topic. What I will present will be, first I will go back a little bit in the history and explain how recent permafrost formed, or the major features of recent permafrost and major amount of ice in the upper permafrost, how it formed, and to understand better the properties of permafrost, we have to go a little bit back because it is geological kind of creature, permafrost. So I will discuss this, how this amount of ice got into permafrost a little bit. And then we will proceed to present day and see how during this period of time permafrost changed in the northern hemisphere. And then we will look at the present state of permafrost. Is it stable still, or there is some kind of problems with it? And then we will speculate a little bit, and I will show some results of some modeling efforts, which could be the possible scenario of changes in permafrost in the future in Alaska for the next, this current century. And then we will talk a little bit about what does it mean for Alaska and for the north changes in permafrost. Again, I will bring some examples. I cannot cover all this topic, it's huge, but some examples I will show you. And I hope you will appreciate it. So again, coming back to definition, so permafrost is product of cold climate. That's why any changes in climate will affect permafrost. And looking back, so here is several scales of changes of climate. So the upper graph is this 100,000 years cycle, glacial, interglacial cycle, big cycles, so-called Milankovitch cycles in climate, which develop huge amount of ground ice sheets and other forms, and then this ice will disappear, and then appear again, and then disappear. So at least in this graph, it's only 4 cycles like this. Now, about 6 or 7 of them documented, and actually there is some records in development right now, which will actually continue this cycle even further in the back. So every roughly 100,000 years, we go from interglacial period like we are right now into glacial period, naturally. So now if you look at the just last 10,000 years, it was generally a warm period of time if you look at the graph on the top. But this relatively warm period is so-called Holocene warm period. It's also not homogeneous. It's also changing in some shorter period of time scale. Climate is changing from colder to warmer, generally staying pretty much warm. And the last, say, 400 years, we experience a relatively cold little ice age, and presently we have enjoyed this warmer period of time. So all this different time scale climate change features affect permafrost. Permafrost reacts to these changes. And immediate reaction of permafrost will be changes in temperature. So changes in temperature of permafrost will come very quickly. But then, a little bit later, with some delay, we'll follow changes in thickness of permafrost, distribution of permafrost. Those kind of changes, they take much longer time than just changes in temperature. And then, and that's I will show you in some data that we collected. So now, how this recent permafrost formed. So we'll start with about 20,000 years ago, where climate was at its maximum, the glacial maximum, the coldest period of time during the last 100,000 years. So permafrost, in this map, it shows only permafrost in the former Soviet Union because we had pretty good data on it. But permafrost was much widespread in that time, and all area which was not covered by thick glaciers was in the northern hemisphere. A very significant portion of it was affected by permafrost. So a very good portion of Europe was under permafrost conditions. And then also in Asia, all Mongolia and down in China, we have also permafrost. And Alaska was mainly not glaciated. It was also all, of course, permafrost, had all permafrost conditions there. Now, with it's not just only widespread permafrost was feature of the times, but also so-called mammoth steppe. So the conditions were very unique. We don't have this kind of steppe right now practically anywhere in the north. But what it was treeless area with very strong winds, very high rate of sedimentation, so lots of sediments were deposited, and very, very harsh climate conditions. And these climate conditions, the ice wedges were growing very rapidly. And that's where mainly where ice, the huge amount of ice got into the permafrost and the upper permafrost, which we are supposed to deal right now with that. So also this figure I borrowed from our Museum of the North University. I just came from there and just took a picture. Also, what is interesting that during this very harsh period of climate, there was very interesting ecosystem there with very tall grasses and abundance of animals, grazers and predators. So what was another very important feature of the material which was collected, sedimented there, it was a huge amount of carbon was sequestered in that sediments. So it was not just ice, but also sediments with very significant portion of it is in form of remnants of grasses, roots, stems even, and sometimes leaves. So lots of carbon was sequestered during that period of time, and that permafrost which also was ice-rich. So these two very important features, they're very important for us to remember because that's lots of ice in this permafrost which was formed during that period of time, and lots of carbon, these two things. Sometimes about 15,000 years ago, the conditions were, climate conditions changed, more or less abruptly. And it's another interesting topic about abruptness of these changes. But for our reason, what we need to know, we start to move from very cold conditions of last glaciation towards warmer conditions of the Holocene. And this graph showing different proxy data which prove this warming effect during this period of time between about 15,000 years ago and 10,000 years ago. Temperature increase was very significant, and at high latitudes it could be as much as 10 or even more degrees Celsius, 20 degrees Fahrenheit changes. And of course permafrost reacted to these changes. So as a result of this warming, by about 9,000 or 5,000 years ago, so-called Holocene optimum, which temperature during that period of time was a little bit warmer, well, a little bit sometimes in some places by 1 or 2 degrees Celsius or 4 degrees Fahrenheit warmer than it is right now. So most of permafrost disappeared from Europe, practically all, and it was very actively thawing around the southern limits of permafrost. So that's where conditions of this period of time. Also, permafrost was formed on ice shelves, which during this cold period of time was land, because sea level was about 120, 130 meters below present day level. So all these Arctic shelves were land, and the same type of icy, ice-rich, and carbon-rich permafrost was forming during that period of time. Now, with increase of sea level, by this time, by 5,000 years, most of these shelves were covered by ocean again, and permafrost is degrading right now, thawing, and this is the process which was very actively developing during this Holocene optimum. This kind of reddish colors on the southern part of permafrost distribution shows that permafrost disappeared from the surface, but still somewhere deeper there. And blue colors, they show that permafrost was still stable. Even in this warmer period of time, permafrost survived. And in Alaska, North Slope, permafrost still stable during this Holocene optimum. However, even in this stable permafrost, some changes, very significant changes, occurred during this period of time. Formation of these thaw lakes, or thermokarst lakes. It was a kind of explosion of lakes in low lands, which thermally permafrost is still stable there. However, increasing in the summer thaw, reached this very icy permafrost, and this ice start turning into water, settlement, and collection of water developed this thermokarst lake or thaw lakes. And these lakes, they're still there since then. So the most lakes on these Arctic lowlands were developed during this Holocene optimum. And they're still changing, some of them draining, some of them appearing new, but the major explosion of number of these lakes happened during that period of time, about, well, around 10 to 7,000 years ago. So as a result, if you look at this graph shows in the middle part is proxy for temperature, for climate. Past on the right, present on the left, but also two graphs. On the top is carbon dioxide concentration, and that's all from ice cores, interpretation data from ice cores in Greenland. And the lower part is methane concentration. And you see that climate and changes in very strong greenhouse gases abundance in the atmosphere is very strongly correlated. So all this story, what I was trying to show you, give us some idea that at least part of this increase in greenhouse gases during the warming period is a result of permafrost dynamics. So during cold period of time, this material freezing, collecting organics, sequestered in the frozen state, decreasing abundance of greenhouse gases in the atmosphere. In a warm period of time, permafrost thaw and ice melting release this carbon again into the carbon cycle, and as a result, the increase in CO2 and methane concentration in the atmosphere. So there's other mechanisms, of course, involved, but our point is at least some of these process and results is the product of changes in permafrost. And some scientists believe that very significant part of this cycle is result of working of permafrost, developing and degrading of permafrost. So after this Holocene optimum, again, some proxy data showing that it was cooling. So last several thousand years generally was on the colder side. And as a result, of course, permafrost reacted. And by now, permafrost reoccupied a significant part of the land which was lost during the Holocene optimum. So this is pretty much present-day distribution of permafrost in northern Eurasia. And if climate, of course, the shelves, they're still underwater. Permafrost is thawing under those shelves, upper red colors. But in the lower part, we have new Holocene permafrost, which formed down to maybe 50 to 100 meters during this period of time. And if climate will not change, that's pretty much what we have. Even with a little bit warmer climate right now than it was, say, 50 years ago, and some permafrost is degrading already, it's still not, we are still in a climate which more or less in equilibrium, permafrost is still in equilibrium with climate, except for some specific regions. So if climate will not change, there will be some changes in permafrost, but not that really significant. However, we know that projections of climate models, and specifically from IPCC report, showing that we should expect very significant changes in warming in climate, especially in high latitudes, up to 7 degrees warming during this century. That's what is projection. Of course, 7 degrees warming is a very significant number, very big number, because the coldest permafrost now in Alaska is warmer than -10. So you can imagine. It's very significant. So to keep track of permafrost and its stability and how it's changed, we are working, as permafrost community, working very hard to monitor, to record temperature in permafrost, because temperature is one of the most straightforward parameter which you can measure, and at the same time it shows the health of permafrost. So if you have permafrost with -5 and lower, that's pretty healthy and stable permafrost. As soon as temperatures start to get to 0 degrees Celsius or 32 Fahrenheit, then you start to have some instability showing up, and there permafrost is not healthy and in danger. So that's why we, as a permafrost community, developed a program, actually it's international program of thermal state of permafrost, where we measure temperature in many boreholes. Right now, after this international polar year was very helpful in this direction, we have about 850 long-term borehole measurements, which we hope to continue to measure in northern well, it's actually global, and most of them in northern hemisphere. So this is an example of our system of deep boreholes where we measure temperature in Alaska. And typically it looked like we have some small met station there, and also we have borehole with cable in it and measure temperature. In this case, automatically every hour. We don't have to measure in deep borehole temperature every hour, but because we measure it every hour for shallow conditions, so we do the same in deeper borehole. And this kind of data provide us opportunity to look at the changes in permafrost. And especially in Alaska, we were very fortunate because Geophysical Institute, by the lead of Professor Emeritus Tom Osterkamp, developed this transect of boreholes. He was very visionary, and he did it in the late 70s and early 80s. And now, since then, temperature was recorded every year. So we have continuous a record of temperatures and permafrost since then. And now it's very unique data. It's very unique not only for United States, for North America, but for Russia as well. So it's one of the very, very valuable records. So now we can compare present-day conditions and future conditions, if these measurements will be continued in the future, how permafrost behaves, where it's going. And this is just one example, one borehole at Dead Horse. It's one of the northern borehole in this transect. So this record started by Tom in early 80s. And you see from there, in the 80s, was kind of, so what we show here is so-called temperature profiles. So the temperature in Celsius on top, the depth on the left. So from 20 meters to 50 meters. So from roughly 60 feet to 150 feet. So every year we record this temperature profile. And what we see in 80s, temperature was kind of varying in the area of -8.5 at this site. And since late 80s, it's warming. It's warming so much that at 20 meters depth, which is 60 feet, we have more than 2 degrees Celsius, more than 4 degrees Fahrenheit warming at this site in permafrost temperature. And even at 50 meters, 150 feet, more than that, we have almost 1 degree Celsius warming. So this definitely show that the trend is warming in permafrost in Alaska. And this is data from other sites on the northern part of this transect, starting with West Dog, the coldest conditions. In the beginning of measurements, we had temperatures below -10. We don't have any more, not from our boreholes, not from USGS boreholes. We don't have any temperatures below -10 degrees in permafrost anymore at the places where we measure it. And then see that most of the changes happened during the 90s. In the 2000s was kind of, there was increase, but very, very small increase in northern sites, and almost no increase in the Brooks Range, or actually it's northern foothills of the Brooks Range. And very recently we start to see something warming again. So it's very interesting. Every year we go and add one more year of data, and it's very interesting to see where it's going on. And it seems like lately there is some acceleration of warming again after more or less stable conditions on the North Slope during the 2000s. So similar data from interior Alaska showing the same, kind of generally the same trend. However, it's less in numbers. So see, this scale is different. It's from -5 to -0.5 to -3 Celsius. So the increase is less than a degree or a degree and a half mostly. But temperature is much closer to zero. And if even in Dead Horse temperature changed by 4 degrees or 3 degrees Celsius at the top of the permafrost, it's still from minus, say, 9 to -6 or -5. So -5 is still stable. So in interior Alaska, it's a little bit more worrisome because temperature is really closing to an instability range of permafrost temperatures towards the 0 degrees Celsius. Another interesting feature here, if you look carefully, you see that during the last several years, it is cooling somewhere there, at least at several sites like College Pit, Birch Lake, Old Man. So it was a little bit of cooling. Of course, this cooling didn't bring back permafrost temperatures from the beginning of these records. But it is some cooling, which is a kind of small cooling bump on global warming trend. An explanation could be found from our records from air temperature on the bottom from Fairbanks and especially on snow depth. So lately we really have most of our years of winters pretty low snow conditions. So that could explain this kind of local cooling of permafrost. But the point is that just continue these records, we really can tell what is going on right now, and especially in comparison with what it was in the past. The results of these efforts brought this snapshot, thermal state of permafrost snapshot for Northern Hemisphere. I will show only 2 examples, one for North America and another one for Northern Eurasia. And so, of course, most of the data comes from Alaska and West Canada because of lots of activities there. And if you look at the colors, show the temperature. So again, cold temperature now we can find it only in a high Arctic and high Canadian Arctic. There are still some colder temperatures in the North Slope of Alaska between -5 and 10, -10. But if you go to interior Alaska and the rest of Alaska, south from the Brooks Range, so most colors are orange and yellow. So most permafrost is within less than 2 degrees Celsius from point of thawing. So that's really gives us idea that of stability, or better to say instability of permafrost in the interior of Alaska. There are still some locations where permafrost is colder than -2 even in the interior, but the most color are orange and yellow, and red represents no permafrost already. And it's normal because it's discontinuous permafrost zone. You can find permafrost and non-permafrost in the same area. So from Siberia, data from Siberia, very interestingly similar to what we see in Alaska. So major warming during the 90s, late 80s and 90s, a little bit of not too much warming in 2000s at some places, some locations, and much more warming in colder permafrost than in warmer permafrost. So that's give us idea that these changes are not Alaska or Northwest North America specific process. It is actually at least hemispherical process. And the same data we have from Nordic countries as well, showing pretty much the same trends. And putting it on the map for Northern Eurasia, the same idea with colors, you see that again the colder permafrost is still only in the high Arctic, high Russian Arctic, and even in continuous permafrost, which kind of dark blue background, you can start to see these little red dots. It means that permafrost is thawing, even in southern part of continuous permafrost zone. It means that boundary between continuous and discontinuous permafrost is moving up north. And we have few examples where we're recording thawing permafrost. And this is one of the sites in western Siberia where it shows development of thawing of permafrost. During the last 40 years, at some locations, the top of permafrost lowered down by several meters, sometimes up to 8 meters during these 40 years. And not only already existing, we call it taliks, developing deeper and deeper, but also in the upper graph showing that permafrost up to beginning of 90s was more or less stable, and then it started to rapidly degrading at this location. So not so many locations in natural conditions, again, natural conditions without any disturbances. It's just a result of climate change we have on degradation of permafrost, because it's not that widespread yet. But we probably can expect that it will happen more and more often in the future if these projections of climate change will show that they make sense. So now, what we can say about the future? Well, we can use all this information what we have to make our models a little bit kind of less uncertain. That's only what we can hope, because models is models. So somebody said all models are wrong, some of them could be useful, right? So we hope that our models are useful. Well, so we do some modeling work, and I will show some results of this modeling with some scenario of climate development. Of course, there is many different scenarios you can choose from. We choose some intermediate, so not too cold future climate, not too warm, somewhere in the middle. So if you follow this permafrost, so this is recent day permafrost distribution in the northern hemisphere. So by mid-century, this all red area is showing thawing of permafrost. Not just warming, all permafrost will be warming, but at these locations, permafrost will be already thawing from the top down in most of the locations. Again, of course, the scale of this map is pretty bad, and there will be some places where permafrost will still stable in this zone, but as a general trend, that's the area which will be affected by widespread permafrost degradation. And by the end of the century, that's projections gives us that more than half of recent day more or less stable permafrost will be degrading on this scale by the end of the century. So we did some work with a higher resolution for Alaska using the same type of modeling and fit these models with our data. And that I will present some results. So we'll start with present day conditions. Red is thawing permafrost, blue is, well, more or less stable, and whitish is very unstable. It's already going, something is there. So next several decades, 2 decades, actually showing not too much warming, especially this recent decade. It's very interesting how these models can produce this kind of climate models, but it's different topic of presentation. We just believe in what climate models produce and use it as input data for our models. But after that, in 20s and 30s and 40s, especially by mid-century, lots of area in south from Yukon River generally, and some places north of it, permafrost will be degrading, widespread. And then by the end of the century, we can expect, well, if this model and climate models are correct, that pretty much all permafrost south from Brooks Range, mostly except for some areas in interior, permafrost will be thawing, actively thawing from the top down. Well, what's the consequences of that? There's many consequences, and we can talk a lot about it. But altogether, I think at this point, the major two which we have to pay attention are 2 of them. So effect of degrading permafrost on carbon cycle. and on permafrost change as societal impact. And I will cover a little bit both of them, but I don't have really too much time to talk about. But I will give you some examples. So let's start with carbon cycle. Remember I said that we believe that during that long period of time, development and degrading of permafrost has something to give to these changes in greenhouse gas concentration. So we still believe in that. And if you look at the material which is thawing now, say here thawing is going on because of the erosion. It's not necessarily climate warming, but erosion. However, if looking at the material, we see that this permafrost, the soil, frozen soil, contain up to sometimes 10% of carbon in it. And of course, this huge amount of carbon returning back into the carbon cycle will produce significant amount of greenhouse gases, or carbon dioxide, or methane, or others. And that could be comparable with what, say, the activities of people, human activities, are producing right now in form of burning fossil fuels. Very important to know which way it will go, or methane. If it will be wetter conditions, this decomposition of this organic matter will produce methane. In drier conditions, it will be mostly CO2. Here it's some couple examples of effect of thawing permafrost on surface hydrology. So you can have this thawing permafrost actually both wetting and drying, depending where you are. What is the soil type? What is the topography? What is drainage conditions generally? In bad drainage conditions, like this example of Tanana Flats, degrading permafrost develop bogs, and boreal forests turning into bogs. So this is a photo by Thor Jorgensen, and you can see it flying to Fairbanks. You know, when you go approaching airport, you see these dying trees there, dying birch trees. And that's because in the past, during the Little Ice Age, it was permafrost there, and surface was much higher because of ice in the permafrost brought it up. Conditions were nice, trees were growing. Now, because of warming, actually, these permafrost start to degrade and go back to bogs. And trees which were developed during this nice period of time, now sorry, but you cannot do anything about it. So that's way where thawing permafrost make it conditions wetter. Other scenario where you have well-drained conditions like sandy soils, higher in elevation, better drainage conditions, thawing of permafrost will lead to drying. In this example is where permafrost degraded, at least from the surface down to several meters, in an area affected by fire in central West Siberia, East Siberia in Yakutia. The soils conditions and topography prevent development of forest again because conditions became too dry for the forest. And forest is changing from boreal forest into steppe, kind of like grassland conditions. So this example shows that degradation of permafrost can do both drying and wetting. This is from Kenji Yoshikawa example. There is more local effects of thawing permafrost. Remember this big ice wedges what I showed before? So now if permafrost is thawing, these ice wedges will melt and turn into water. Surface will subside, collect water. This water will warm up again. So it's kind of positive feedback. And eventually development of thermokarst lake or thaw lake. And that's very typical process which, like I said, the most actively was developing during the Holocene Optimum. But now this new wave of warming, this process getting more and more active again. So it starts with small depressions like this, and then it turned into thermokarst lakes. And these thermokarst lakes producing lots of methane. So there is lots of work was done by the University of Alaska Fairbanks, Katie Walder specifically, and colleagues, showing that it's really a significant source of methane, all these thaw lakes in the area of permafrost. So that's very important part in recent day carbon cycle. Slow processes also trigger some degradation of permafrost, and again, involvement of carbon from the frozen state back into carbon cycle and producing greenhouse gases. This example from Banks Island and the Canadian archipelago, and this is one of this very picture I like, this kind of slide of upper soil, develop this kind of carpet fall feature, very interesting. But what is going on after that, this it will develop this small thermokarst lake, and this is already north slope of Alaska, and you see the water is very brownish, there's lots of carbon there, and it smells like in the permafrost tunnel. I don't know if you were in permafrost tunnel, it smells pretty badly right there in open air. So lots of carbon again from that sequestered state in permafrost returning back into carbon cycle and emitting as a greenhouse gases. And just to show what is the scale, I mean, the process is understandable, but if it's important, well, if you look at the recent estimates, and it's also a result of activities of permafrost community during the International Polar Year, there is estimates how much carbon is sequestered now in the permafrost area. So it's about 1,000 gigaton of carbon in the upper 3 meters, and another 650 gigaton in the deeper permafrost. Just for comparison, it's about the number, about 700 gigaton is now in the atmosphere. So in this permafrost conditions with frozen carbon is actually twice more of the carbon in the frozen state right now, which we know about, compared to amount of carbon in the atmosphere. So if all this carbon will be released, which is of course very not possible scenario, but if the concentration of carbon dioxide could be actually tripled in the atmosphere. Well, of course, it's probably not possible scenario. And then there's even deeper sources of carbon, and not just carbon, but maybe methane and gas hydrates and all this kind of huge amount of carbon sequestered in permafrost, in the deeper permafrost, and under permafrost, which very not good estimates at all, and several order of magnitude range estimates. But the amount of this carbon could be even larger than in upper permafrost. So that's another source which probably will be involved in a much slower way than its upper permafrost carbon, but eventually it became a player, significant player in carbon cycle. So that's all about carbon now, societal impacts. And well, I don't have too much time, but I have lots of interesting pictures to show, and mostly it will be pictures, actually. So, again, the major thing is ice in the permafrost, specifically massive ice. So this is example from Fox area in Fairbanks, north from Fairbanks. So this is a big ice wedges. Again, if somebody had a chance to visit a permafrost tunnel, we could see this ice wedges from inside. So this is from some cliff. This is ice wedge. You're looking along the ice wedge here. So it's still lots of ice there in many areas around Fairbanks. Some of this ice already melted in the recent past, and when it happened, then this ecosystem sitting on this very icy permafrost just collapsed. And this is a good example. This Kenji Yoshikawa is for scale. This thermokarst developments in, again, the same area. So you can see the forest practically destroyed when it happened. If ice wedges close to the ground, you see this kind of effect, and this is it's Baleine road bicycle paths. Very fun to ride these bicycle paths, and they tried to fix it, more or less periodically, but it turned back to the same conditions because this ice wedge is close to the surface. When they start to melt ice, where ice wedge is, subsidence is much larger than in between ice wedges. Remember one of the first slides I showed looking from the top, that ice wedges develop in some kind of some polygons. So if you cross these polygons, ice in wedges will start to melt. You will have this kind of topography or microtopography. So ice melts and surface subsides in ice wedges, but in between there's much less ice. So you have this kind of fun to ride. And also along the Farmers Loop bicycle path, in some places you can see similar things. So it's pretty much a similar place. This tree is leaning. It fell down some times ago, so it doesn't exist anymore. Even not in a bicycle path, it's on another side of Baleine Road. It's a snowmobile, snow machine path, showing the same feature. Again, lots of fun, I think, to ride. And you see that it's this degradation of this ice wedge is triggered by Baleine Road. So it's not global warming, really. But if you look, this kind of troughs, they're going into the forest already. So there is some developments in the forest already, which not directly impacted by this road. If ice, big mass ices, chunks of ice are deeper in the ground, this ice could melt some times ago, say 10, 20 years ago, developing some voids under some soil on the top. And these voids can be preserved for a while, and maybe for many years. However, these voids were developed on these ice wedges. And remember, they're all developing this kind of network. So they're all connected. So the voids, not just simple hole in the middle of the ground, but it's in the form of channels. And water can move through these channels. And water can increase this volume of voids. And eventually, sooner or later, the surface collapse. And we very well know sinkholes. Sinkholes around Fairbanks, it's typical, especially in the spring when there's lots of water there. So this one is a sinkhole along the Gulfstream Road. And it's pretty deep. Well, I'm trying to reach with shovel, but it's about 2 meters, so 6 feet deep, and sometimes even deeper. And the most interestingly, there's lots of water in spring coming in this sinkhole, and the level doesn't increase. It's water really draining somewhere. So this water will not collect and will not fill this deep or sinkhole because of this connection. So it will drain somewhere. It will be interesting to make experiment and see where it comes out of the ground. And there are some ideas about, but probably people who live downslope will not appreciate these ideas. Put some kind of radiative material there and see where it goes. Radioactive. And this is right on the shoulder of Gulfstream Road. One hole appeared like this. And again, you see water coming in and disappearing. Like this. So, of course, all this process will affect infrastructure. And again, infrastructure itself is huge, has huge impact on permafrost without any kind of warming of climate. However, it's all happening on the background of kind of background temperatures. If background temperatures of permafrost higher, this process could develop more easily. And this is just a few examples, most of them from Russia. Starting from the top left, this building was never actually occupied by people because it was built on half permafrost and half non-permafrost conditions without any precaution. And by the time it was almost completed, permafrost thawed, and the one portion moved down about 2 meters, not 2 meters, but about 1.5 meters, so about 3 feet, 5 feet down, and it was crack in the middle, and of course it was never occupied by people, so it was just demolished. Pipelines in Russia affected by erosion and because of thawing permafrost without any precaution was built in a hurry in 70s and 80s. Lower right is from Chersky. This interesting building, first some cracks appeared on the walls, And in less than a week, just a few days, whole section of this house just collapsed. Of course, people had time to leave, but if you look carefully, there is some belongings that were still there, so not everything was removed from it. And this collapse was a result of thawing of permafrost. The thawing of permafrost was not really 100% triggered by, well, even less than that, by warming, but by leaking hot water in the basement of the building. So it's bad maintenance practices. It's not climate change. However, it's good kind of demonstration what will happen to buildings with even good practices, but with disappearing permafrost. So you can still have some problems here. And finally, on the right up corner, that's here. It's a back parking lot at the Geophysical Institute and Arctic Research Center. So West Ridge, northern parking lot. And I have a whole story about this parking lot, so I will show you briefly. So whole history I demonstrated. I called it University versus permafrost. So who will prevail? So it started in June 2000. So a new building was built just recently, this International Arctic Research Center on the right, Geophysical Institute on the left, and big parking lot on a place which was small, very small gravel parking lot of the Geophysical Institute. So most of this part was forest. So it was cleared, leveled, and put asphalt. So small holes appeared like this. First it was kind of, well, holes, not so much problem. But the same year, later in July, suddenly the surface collapsed and developed a huge sinkhole there. And I heard a story from one of my students that he was at the fire department that time, and they brought a truck full of water and dumped in this hole just to look how big it is. And all water disappeared without any traces. So they helped to further process probably as well. So now, interestingly, that in 2003, a new project started right there. That now is VERB, West Ridge Research Building. And when the contractors start digging this pit, I will come, more or less periodically and say, did you see any holes there? Then they said, no, we don't need any holes here. Get out of here. So anyway, when they were digging far enough from the Geophysical Institute towards the forest, they eventually, on the right lower corner, they discovered this hole. Hole which is kind of like tunnel going somewhere. And so people start to a little bit worry about it, but they still digging. And the same holes appeared on another side of the pit as well. This is Professor Yuri Shur looking at this hole. And it's very interesting. You look at this hole and you see these tunnels. They all connected and it goes somewhere far, far, far. So it's really interconnected tunnels. It's not just voids. Well, digging farther, they found ice. Finally. First it was just small piece, and then suddenly, boom, it's all ice wedge, nice ice wedge, about 3 meters or more in width, and going somewhere down. So at this point, there was some kind of, well, not panic, but some. So they stopped digging and drill more holes to look what is that. And after this drilling, they said, well, it's just a small piece of ice. We will just dig it out and everything will be good. That's they did. So 2003. By the end of 2003, this pit was completed, and in August, the building started to getting some shapes already. Well, in August, right above this ice wedge, the new collapse appeared right there, right next to the wall. And if you look, it's pretty much the same feature. So they look pretty much the same. Typical sinkhole going down 6, 8, sometimes even deeper feet. Well, it was filled with material, and warp is there, and so far it's okay. However, in May 2004, some new holes, you remember these holes, just looking very innocent first, start to appear on the wall towards the forest, and of course, soon enough, the new sinkhole developed. And it's nice to see this picture was made practically from my office, so it's very easy to monitor these things. So of course, immediately several trucks, many trucks with gravel came and filled this hole, and everything was good. But 2006, another hole appeared. So fortunately, farther. So it seems like a university is winning here, right? So it's moving farther into the forest. Well, who cares about forest? There are some small buildings there, but it's and also also at the very first hole I showed, exactly the same location, new hole appeared again, 2006. Well, you can see this settlement right on the parking lot, and you can trace, if you look from high enough, you see this polygonal shape of this truss. So it is melting ice there, melting ice wedges, and settlement will continue. So far, it was 2006. If you look now, it looks pretty good because there was some money was spent and parking lot was fixed. However, especially with further warming, you should expect this story, university versus permafrost, will continue. And I promise I will, as far as I am there, I will keep recording this. And just last few slides here on other, maybe more serious topic. With all this warming and thawing, projected thawing of permafrost, by the end of the century, many villages especially in the northwest of Alaska, will be affected of this widespread thawing of permafrost. And practically Kivalina, Point Hope, and many other villages there will turn from more or less stable permafrost now, which is about -3 degrees Celsius, to thawing permafrost by then. It's already, at least 12 villages have big major problem with erosion, coastal erosion, both ocean coast and river banks. And at least 12 of them already have some plans for relocation. But with relocation, it's another problem, where to relocate. Permafrost is around, so how to solve this problem? But other problems related to water supply. So many villages in the northwest, again, use or rivers or lakes for water supply. And this further degradation of permafrost, we start more and more see this very significant coastal erosion or banks erosion on the rivers, where again, if you look at this right low corner, this icy and also carbon-rich permafrost is thawing, supplying this sediments with something which you don't know even what is there chemically and biologically, really, into water, which it's Willock River, and which supply water for Kivalina. And also this slides or development of probably possible solution as well, to be sure that because there is permafrost as well under the building, but it was not icy at all. So it seems like that permafrost thawed sometimes in the past, and then refreezing, it didn't get any significant amount of ice there. So the problem only the very, very far north corner. But so far it seems like it's pushing into the forest, which, like I said, maybe a university is winning in terms of building, but parking lot, of course, will be a problem for a while.
This is in regards to the remote lakes or whatever. I live in a very remote lake. And so it's actually a two-front process. With the melting permafrost, you can have the silt and other things or polluting the water that we drink. And also the lake could find one of those channels and go away suddenly, because we've seen a huge drop in our water. over the years, and everyone's kind of, some people say from the '64 earthquake, but it's been even more dramatic. And I'm not believing the earthquake thing where it opened a channel. I think now it's permafrost. Well, what do you do?
Yeah.
Do like the university, just bring truckloads in of dirt? No,
well, first of all, I think you have to get more information on specific, location, specific lake, how stable it is, and you can use some methods, remote sensing, to look what lakes are doing around it. Do some analysis and see if any chance that there is some channel where a lake can drain. What is topography? There is some way to predict how stable this lake is. Of course, warming in water temperature, you cannot do too much, and development of some algae and all these creatures there, it's very difficult to do. So you will still have some problem with quality of water, but at least you can predict if lake will stay there or you have some problems in the near future.
Well, this was Lake Minchumina, and you dudes were out there a while ago. We had Russian people out, and they were doing some measurements. It was a few years ago. You were helicoptered in. Were you one of them or no?
No.
Oh, it was some.
I'm Russian, but not those ones. Yeah, it's a major problem. It could be larger because the rate of lake disappearance is very worrisome. Yeah.
I was surprised to see or hear the mention of Kazakhstan and then the Nepal plateau permafrost issues. Are they similar to the things you were talking about here today, or is it a different kind of geographical issue?
Yeah, it's mountain permafrost, so it's pretty much different in general. So it's much more diverse and variable in space. Lots of bedrock, which doesn't care if it's above zero or below zero. However, there is some very interesting other problems which actually can help people a little bit. So you know that from this area, the problem is also fresh water. And most of this fresh water is coming from glaciers. And this glacier is very, very rapidly disappearing in this area, especially in the Central Asia. And not in Himalayas yet, but in Central Asia it's getting real problem because it directly relates to fresh water source. So now having permafrost there, it could help. It will not help a lot. I mean, it will help a lot, but for a short period of time. So thawing permafrost with lots of ice in it can, for some period of time, feed these streams of fresh water from the mountains. But it's also very limited. It's maybe even more limited than glaciers. So in this case, they're very interested in permafrost in terms of source of fresh water. In alpine permafrost in Alps, there is another problems with hazards, geological hazards, because thawing permafrost, again, this holding capacity of the material degrade immediately after thawing, and developing all kind of slides, rock falls, all kind of things, and because it's highly populated area compared to Himalayas, so that's every event is hazard, and of course some tourist industry all kind of affected. So they have all looking very carefully on permafrost development and invest lots of money actually in a monitoring system in Alps. The next question.
Thank you. Just had a question building on the previous one as far as earthquakes. How are earthquakes included in the modeling, and what happens in some of the different environments when an earthquake happens as far as the water percolating up, and where does the water go, and if that has any implications for Fairbanks? Yeah,
well, it's not in a model, I can tell immediately, and it's probably something which we will get to much later than we will try to include something else in the model. So they really so far developed very kind of, well, I wouldn't say primitive, otherwise I will kind of shoot my leg or whatever. But so earthquakes have some some engineering consequences in terms of stability of soil, especially if in permafrost regions there could be conditions where soils is oversaturated. In this case, of course, there can be a cumulative effect and amplifying of earthquake in these locations. So this is a very interesting problem. We are not dealing with this one at all. So it's a very interesting topic. We just don't have capacity to answer these questions. But in terms of kind of general permafrost conditions, of course, earthquake is minor factor.
Thank you. I understand that last night DOT had a information hearing on a road to Nome, and so I was paying attention to your maps there, figuring out where Nome was. And in your opinion, does it make sense financially to build and maintain a road across that discontinuous permafrost?
Well, I think so. Without roads, it's very difficult to live. It will cost, and it will cost more farther we go. So probably my recommendation will be build now, because later it will be even more expensive to build.
I think we have one last question here in the back.
So on that road to Nome, sorry, hold on a second. Anyway, on the road to Nome, because I know they've started using styrofoam and road bases to basically have the road actually float on, sit on the styrofoam, which actually allows it to basically float on top of the soil. So that way, I mean, would that be a useful solution for the permafrost, or would it be kind of pointless because of the basically sinkholes that would develop along the road?
Well, of course, the major thing is how much ice in there. That's the first question to answer. And of course, avoid, if possible, any ice-rich permafrost, which is impossible, and somewhere you have to cross this bad conditions. But building practice of building without disturbances, or minimal disturbance. Of course, you cannot build without disturbances, but minimal disturbances, and putting this insulative material will actually help, because what you do, you reduce the heat flux into the ground, and you postpone, and sometimes a lot, postponing this process of thawing of permafrost. Of course, with all warmer climate, you will start to see some side effects. And permafrost, maybe you can preserve permafrost right under the road using all kind of engineering solutions, but permafrost around the road will start to thaw and start to develop all kind of processes, these sinkholes or slope processes. It always has to be taken into consideration in engineering design. But like I said, I mean, engineering design is developed well enough to do it and solve problems. The question is how much, I mean, how expensive it will be. That's the question.
Thank you. Will you all join me in applauding and thanking Dr. Romanovsky one last time?
Yeah, thank you very much. Thank you for coming.
Thank you all for coming out tonight.